أرحب بجميع زملائي اللي شرفوني وكافة الحضور اللي شرفوني بحضور محاضرتي حول الماس سبيكترومتري اللي تتضمن تعريف الماس والبرنسبل اوف ماس والابليكيشن والbeneficial side of using of mass. What we mean by mass spectrometry mean we are going to have a molecule of compound, and this molecule of compound undergoes degradation and forming a type of a fragment, and we are going to accumulate these fragments in order to reach the acceptable structure of our chemical compound. The mass technique is completely different from IR, from NMR, from UV. All these three techniques involve the absorption of energy and emission of energy. Whereas in case of mass, there is no absorption of energy or emission of energy. The principle of mass is depend, as I'm going to explain it here, is depend upon electronic bombardment of the molecule by electron, and according to this bombardment is going to lose another electron and forming molecular ion. This molecular ion is unstable and undergoes to degradation into free radical and cation. And we can say if this free radical as A composition and the cation as B composition, I can rewrite it in another way as B will be a cation one time and a free radical at the second time, and the same case with A. That's the instrument of mass. First of all, our compound should be as a gas state, and if it's not as a gas state, as we are going to enter it within the instrument, it should be converted into gas. Otherwise, our essential compound, we cannot use it, and we are trying to synthesize or prepare a derivative for it and carry out the measurement of mass. With mass, we are going here to subject our compound by a magnetic field, and we are going to have three types of cations. One of them which is suitable to reach the detector, and by another way it will be recording by the recorder, and the another one will be as a heavy one, and the third type as a heavy one, light one. Both of heavy one and light one has no ability to reach the detector. And by another meaning, it will be not appear here within the spectrum of mass. Why? Because the heavy one is like a fat person. When he's running, he have no ability to reach the end. And the same in case of light one, like a thin person, he have, when he going to run, he run rapidly, and he also cannot reach the detector. So how we can make the heavy one and the light one reach the detector, and by another meaning, it will be appear here within our spectrum. We say that we have here magnetic field. So by the management of magnetic field, one time I going to increase it, and by the way, I help the heavy one to reach the detector, and the another one, I going to help the light one to reach the detector by decrease the magnetic field. By decreasing the magnetic field, by another meaning, I going to decrease the rate of light one and can reach the detector. With mass spectrometry, we have two types of resolution. One of them simple resolution, and the another one high resolution. How we can calculate the resolution? We calculate it by calculate the ratio of Mn, which is mean the high mass number, and the differentiation between Mn and MM. MM here mean the lower mass number. We are going to choose two neighboring peaks the two neighboring peaks at the same time, they must be the highest two peaks. And we are going to carry out our calculation to find the percentage or the ratio of resolution. We can regard the low resolution as we are when we are going to make any calculation, we are going to have integer number. But in case of high resolution, I'm going to have, like when I carry out my calculation, I'm going to have fractions. Sometimes I should use high resolution. When? If there is high differentiation between the molecules, I can use low resolution. But in case if my probabilities is about CO, N2, CH2N, C2H4, all of them, like here, all of them have so close molecular weight. So it's not useful for me to use low resolution, because low resolution going to give me integer number. 27.9 will be as a 28, here will be 28, the same with these two cases. So I should use high resolution. By another meaning, when I use high resolution, I'm going to have fractions. So if I get the number 28.0, I have my probability as N2, CH2N, C2H4. I'm going to next number. If the next number will be 0, I know that I have N2. If the next number is 1, I know that I have CH2N. In general, we have two types of technique with mass. One of them, electron impact, which is the most common one, and the second one, chemical ionization. Electron impact involve, as I said before, electronic bombardment, and we are going to have molecular ion. Whereas in case of chemical ionization, there is no ionic bombardment, there's no electronic bombardment. There will be a type of ionization, and I'm not going to have molecular ion. I'm going to have molecular ion plus 1, which is equal to proton of hydrogen. Which one is more beneficial for me? If I can detect the molecular ion clearly, electron impact is the more benefit for me. But in case if there is complicated or it's so difficult to detect the molecular ion, electron impact will be not useful for me. The most useful one will be chemical ionization. How can I read the spectrum of mass? I have the relationship between relative abundance and M over Z. M over Z mean molecular weight over the charge. The charge always equal to 1. Now, I have molecular ion peak, which will be at the end, and maybe I have M+1 peak, which is related to the appearance of carbon-13, the isotope of carbon, and I have base peak. What I mean by molecular ion, it's mean the same molecular weight. There is no difference between the chemical structure of molecular weight and the chemical structure in case of molecular ion, except the losing of electron. So when I write this chemical structure by this way, I should write molecular weight. But if I put it between two brackets and here I write positive dot, it's wrong to write molecular weight. I should write molecular ion, and I write M over Z, which has the same value of molecular weight. The base peak is the most intense peak. By another meaning, as I said before, here we are going to have different types of ions. The technique of mass will be record the type of cations only, not the anions, not the free radical. So just the cations. So when I say here, I have the most intense one, which is referred to base peak, I mean the most stable carbocation. As the carbocation more stable, that give me the most intense one, and I can regard this peak as complete percentage, as 100%. And according to this peak, I going to management the another peaks. As I said at the beginning here, that the electron impact mean that I going to have electronic bombardment for my molecule. So from where the electron will be favored to be loose. If my chemical compound consists only sigma bond, of course it's going to be loose from sigma. But if my compound consists sigma and pi bond, we know that sigma bond mean electrons which tightly bonding together. But in case of pi bond, the electrons not tightly bonding together, just as in case of sigma bond. So in case if my compound consists sigma and pi bonds, whatever the pi bond between carbon-carbon or carbon-oxygen, carbon-nitrogen, whatever, you have pi bond as double bond, as a triple bond, the favorite position to lose the electron will be from pi bond. But if I have sigma bond and heteroatom like oxygen, nitrogen, sulfur, phosphorus, each heteroatom consists non-bonding electrons, as we said, as lone pair of electron. Lone pair of electron, non-bonding electron, so easily to be loose. So the favorite position for losing the electron will be from heteroatom. So in case if my compound consists sigma bond, pi bond, and heteroatom, the favorite position will be not pi bond. It will be the heteroatom. What information can I get it from the determination of mass? I can get the molecular weight, chemical formula, structure, molecular formula, structure. I know if my compound consists isotope and or not, as we are going to see later, and the protein sequence. Now, what are the problems that conjugated with our determination of mass? First of all, maybe I have here the appearance of more than one peaks. If I get M plus 1, as I said before, it will be related to carbon-13, which is the isotope of carbon. But if I get M3 till M14, that's mean I should check out my compound if it's pure or not. Maybe it consists impurities. Or if I be sure that my compound is pure, I should check my detection about the molecular ion. Maybe it's not the molecular ion, it's a type of a fragment. Now, if I fail to detect, as I said before, detect the molecular ion by another meaning, I cannot use electron impact. The favorite one will be used the chemical ionization. Some compounds, the molecular ion its appearance will be so small, it's not clear, that in case of alcoholic compound, the most intense peak will be related to M-1. By another meaning, the deep protonation of hydroxyl group. The stability, of course, is related, if my compound consists aromatic compound, it's related to the formation of a stable carbocation, as it appears here. If my compound consists aromatic ring, that's mean I'm going to have benzylic carbocation, as I said before here, that the detector will be detect only the positive charge cations. So if my compound consists benzene ring, that's mean I have benzylic carbocation. Benzylic carbocation, that's mean high structure of resonance, By another one, it's stable carbocation. The second stable one will be conjugated alkene. By another meaning, I'm going to have allylic carbocation, which also consists conjugation, consists resonance, but the resonance structure will be lower than in case of aromatic one, then the cyclic one, and if consists sulfide or the small types of alkanes. If I cannot recognize the molecular ion, it's mean problem for me. And the appearance of detection of molecular ion will be degrees according to this sequence. If I have peak which is equal to 18, and I have a compound which consists hydroxyl group, 18 mean there is a probability for dehydration, for losing of water molecule. If I have peak related to 31 and my compound consists methoxy group, that's mean I'm going to lose this methoxy group. In case of halide give the type of peak which refers to the halide itself. Like in case of fluoride, I'm going to have 19, or hydrogen fluoride, I'm going to losing of 20. If the compound consists oxygen, like in case of alcohol, in case of carboxylic acid, I should have put in my mind that I'm going to have a probability for the losing of hydroxyl group, which equal to 17, water, which equal to 18. As I said before, that in case of chemical ionization, I'm not going to have molecular ion, but I'm going to have M+1, and I say that one is going to refer to proton of hydrogen. By another meaning, I'm going not to have molecular ion, but I have a quasi-molecular ion. That means it divides me. That's I consider it. I saw that this one will be appear at the end of the chart, and I say, oh, that is the molecular ion, but really it's not the molecular ion. It exceeds the molecular ion by 1. So I should take care in case of using chemical ionization, the appearance one not to divide me, because it's not really the molecular ion. We have a rule of nitrogen. By another meaning, the rule of nitrogen give me initial prediction about my chemical compound. If my chemical compound consists odd number of nitrogen or even number of nitrogen, and at the same time I can have an idea about the molecular weight. So if my compound consists odd number of nitrogen, that means the molecular mass will be odd, and the vice versa will be correct. And if my chemical compound consists even number of nitrogen, that means the molecular weight will be even. Like here, we have 1 nitrogen and the molecular ion 45. We have 2 nitrogens and the molecular weight 60. And the vice versa, here I have the molecular weight, or by another meaning, the M over Z equal to 93, I have 1 nitrogen. I have 138, I have 2 nitrogens. 183, I have 3 nitrogens. But I should put in my mind that 0 will be within the even number. So if my molecular weight even number, I should put in my mind either my compound consists even number of nitrogen or there is no nitrogen, because 0 within the even number. How can I get information about the chemical formula, about the chemical structure of my compound? I can get it by index of hydrogen. Index of hydrogen deficiency give me an idea if my compound, saturated compound, or consists double bond, or ring, or aromatic structure, or maybe aromatic with double bond, as it's going to be explained with another sheet. Now, that's the rule we are going to apply it to calculate the index of hydrogen deficiency. In case, if I calculate the number of hydrogen deficiency and my number is equal to 1, that means my compound either consists one double bond or one ring, not both of them. But if the calculation from index equal to 2, that means either I have with my compound, I have one triple bond or two double bonds or two rings or one double bond plus one ring. If I get number equal to 3, 3 mean either I have with my compound two double bonds and ring, or I have one double bond and one triple bond, like here. But if my number is equal to 4, or any number more than 4, that means I'm going to have benzene. Let we get this one. For example, if I have this question, that's it, my chemical formula. I have here carbon equal to 13, hydrogen 9, nitrogen 2, oxygen 4, brom 1, and sulfur. My rule is that index of hydrogen deficiency that refer to type of atoms which has 4 oxidizing number, like carbon or silicon. So here I have 13. The union will be 9 hydrogens plus 1 brom, because brom also union, divided by 2, plus triple 1, I have nitrogen, 2 divided by 2. The bivalent will be neglected. I don't take care about it. Plus 1, it's equal to 10. Now, I get it, it's equal to 10. I'm going to think. Now, I'm going to think. How many 4 within 10? 10 minus 4, it's equal to 6. That means I have benzene ring. Now, within 6, I can get another 4. That means I have another benzene ring equal to 2. What are the probabilities of 2? Either I'm going to have 2 double bonds or 2 rings or ring plus double bond or triple bonds. So I have here 2 rings. Each ring consists 6 carbon atoms. 6 carbon atoms plus 6 is equal to 12. So from 13, I'm going to have only 1 carbon atom. Here I'm going to have N2O4. N2O4, it's mean 2 nitro group, NO2. And I have brom, sulfur atom, and 1 carbon. That's mean 5 substituted group. Each benzene ring required 6 hydrogens. 6 plus 6 will be equal to 12 minus 5 here, it equal to 7. How many hydrogen atom I have? I have 9. 9 minus 7 will be equal to 2. So in this case, if I put carbon here as a terminal, it should be terminal methyl group. I just have 2 hydrogen, so I cannot put it as a terminal. Sulfur should have 2 bonds, so I should put it here. Now, can I put brom here and nitro group here? Sulfur has lone pair of electron. So the favorite structure that I put the electron with the drawing groups on the ring that bonded to heteroatom in order to decrease the deficiency of electrons and halide within the another one. What about the calculation of the structure, how I can find the molecular ion, how can I find the structure of my compound? That can be done by rule of 13. What's mean the rule of 13? Rule of 13 mean I should have the molecular weight of hydrocarbon, only the hydrocarbon, and I divide it by 13. I'm going to have here integer number with the fractions. The integer number will be referred to the number of carbon atoms. So first of all, I should have the number of molecular weight which corresponding the hydrocarbons only. Divided it by 13, I'm going to have integer number with the fractions. I just take the integer number as a number of carbon atoms within my compound. How I can get the number of protons? The number of protons, I can get it by take the fractions and multiply the fractions by 13. Then I added to the resulted number the number of carbon. Here, 106 divided by 13 equal to 8. So 8.153, 8 means the number of carbon. I will take the fractions 0.153, multiply it by 13, and add the number of carbon to it. I'm going to get the number of hydrogen. What in case if my compound consists heteroatom? I should subtract the mass of heteroatom, because as I said before here, I should have only the number which related to the molecular weight of hydrocarbon. Like in this case, if I have a compound which have molecular ion peak at M/Z equal to 102, and here give me an information that my compound according to FTIR give me strong peak at 1739. 1739 refer to that I have ester group. Ester group mean my compound consists 2 oxygen atoms. So this molecular weight, not a molecular weight for hydrocarbon, So I cannot apply rule of 13 directly. I should subtract from it what is corresponding to the molecular weight of 2 oxygen atoms would equal to 32. Then the resulted number, that's mean the molecular weight of hydrocarbon. I going to apply the rule of 13. Now, is the rule of 13 is useful for me in all cases? Some types I going to have the first number as fraction high number. Like here I have 8.1, it's small number, but in case if I have 8.7, 8.8 or 8.9, it's not useful for me to use rule of 13. I should multiply my calculation with a factor, or I can use easier method than this. Like in this case, look here. If I say that if I going to apply rule of 13, I get number that greater than the expected or acceptable number of hydrogen, how I can get the number of carbon and the number of hydrogen within my compound. From here, I have a compound, and this compound give me this percentage of peaks equal to 77, 112, 114. Look, if I have 2 peaks and the differentiation between them equal to 2, by another meaning, 112, 114, the differentiation between them only 2. That's mean I have isotope related to halides. That's mean within my compound and I have halide. If the ratio is 1 to 3, 33, 100, that's mean the type of halide will be chlor. What chlor equal to what? It equal to 35. It have another isotope which is equal to 37, but which one is the more abundance one? Is 35. So I going to subtract 35 from 112. I going to get 77, which is equal to molecular weight of hydrocarbon. Now I want to try another method than rule of 13. I going to think, within 77, how many number of carbon atoms will be? Each carbon atom is equal to 12. So I going to think, the number 77, how many 12 I can get within this number? I going to have 6. Each one carbon atom equal to 12. If I have 6, it will be equal to 72. So within the 77, the carbon consumes 72. So the number that I have as a differentiation between them will be related to the number of hydrogen. So I conclude the chemical formula as C6H5Cl. To get the information about the chemical structure, I going to apply and calculate index of hydrogen deficiency to conclude the informations about my chemical structure. Can I get information about my compound to calculate the percentage of composition? Like in case of here that I have aspirin compound and the aspirin compound with this chemical formula, and I want to have an idea about the percent composition. The molecular formula appear here for me, and that's the molecular weight. Each carbon equal to 12, hydrogen to 1, oxygen to 16. So I going to divide it, the number of carbon over the total molecular weight. 12 by 9, 108. 1 by 8 is equal to 8. 16 by 4 is equal to 64. Multiplied by 100 also to get, in order to get the corresponding percentage. Now, if I want to get information about the chemical formula from the percentage of composition, how can I get it? Like, if I have the information about my compound, that it consists 40% of carbon, 6.71 hydrogen, 53.28 about oxygen. Again, carbon 12, hydrogen 1, oxygen 16. So I'm going to say that 40 of carbon will be divided by 12. 6.71 of hydrogen divided by 1, 53.28 of oxygen divided by 16. So I'm going to get 3.33, 6.71, 3.33. Which one is the greatest one, or which one is the smallest one? The smallest one will be 3.33. So I'm going to divide each percentage by the smallest one. So I'm going to divide 3.33 by 3.33, 6.71 by 3.33, 3.33 by 3.33. I'm going to get the ratio of carbon will be equal to 1, hydrogen equal to 2, oxygen equal to 1. So I have the chemical formula of my compound, which equal to C1. Of course, I'm not going to write number 1, H2 and oxygen 1. That I said before, that in case if I have a type of isotope, in case of bromine or chlorine or iodine or fluoride, fluoride will give me a peak which related to M-19, iodine which give a peak which equal to M-127 or 27. And in case of iodine, I'm going to find large gap between molecular ion and another peak rather than the peak that related to iodine. What about sulfur? Sulfur also give me the same case of halide, give me 2 peaks which is related to M and M+2. So how can I know that I have sulfur rather than halide? Look, the ratio between M+2 and M+2 is...
آسفة دكتورة تغريد على المقاطعة، لكن الشير ما واضح.
الشير ما واضح؟
اي ما جاي يتقلب، ما جاي يتقلب دكتورة تغريد عيني.
يعني وين الخلل؟
بس دكتورة تغريد سوي ستوب شيرينج وبعد ذلك سوي شير مرة أخرى إذا أمكن.
أوكي هسه دقيقة. هي المشكلة اللابتوب شكل. هسه ما واضح عيني؟
لا عيني دكتورة تغريد ماكو حبيبتي.
دقيقة عيني. دقيقة. هسه سويت ستوب شيرينج.
تغريد مرة ثانية سوي شيرينج.
ايه عيني ايه دقيقة. هسه راح اسوي شيرينج مرة ثانية، خلي افتحها مرة اللغ حتى تكون شوية اوضح. هسه هم واضح؟
لا واضح دكتورة تغريد، لا عيني واضح.
دا يتقلب؟
بس نزلي هذا الزوم دكتورة تغريد، بس نزلي الزوم. اي 10 دكتورة.
دا يتقلب عادي. اوكي يعني من هنا لو من وين؟ يعني من هنا ابدي همينه لو
لا النافذة اللي كنتي بها اي اللي استقطعتي من يمها دكتورة التغريد.
Okay. Then, in case of silver, that we found that the ratio between M+2 and M+2 is so small than acceptable, so small. So that's mean if I have a chart which have or consists M and M+2 and the M+2 is so small, that's mean I have sulfur. In case of bromine and chlorine, which is the two common halides within our compound, if the ratio of the peaks of M and M+2 is 1 to 3, or the percentage is 1 to 3, that means I have halide, as I said before. But if both of them close together as a peaks or as a ratio, that means I have bromine. What are the type of cleavage? Maybe I have a type of cleavage which is referred to sigma and to alpha and beta. Sigma, that means sigma bond is going to break down. But from where the sigma bond is going to break down? Shall I carry out the cleavage from here or from here? The cleavage will be taking place from the positions that led to the formation of most stable carbocation. As the stable carbocation will be formed, that means you are going to get the appearance of intense peak. Like in this case, I going to have secondary carbocation. Whereas if I write methyl group as a carbocation, the appearance of this peak will be not intense, not clear, because methyl is primary carbocation. Also, I have another type of a cleavage, which is so important cleavage in case of carbonyl compound, even ethers, halide, alcoholic amines, which is alpha cleavage. And also, I'm going to explain later beta cleavage. What mean by alpha cleavage? When you hear alpha cleavage, that means alpha carbon will be not within the fragment which hold the positive charge. Like here, look, that's the active group. That's the first carbon atom bonded to active group. So this carbon and alpha carbon, and also this carbon and alpha carbon. So from alpha cleavage, look, alpha carbon will be not within the species as a positive charge. This type of cation is an acylium ion. Acylium ion will be, we can write it as CH3, C positive, double bond oxygen. And of course, we are going to have resonance by the lone pair of electron of oxygen, which led to the formation of this stable structure of acylium ion. Again, can I carry out alpha cleavage from the another position of alpha carbon? The answer will be yes, I can do it. And the same way, alpha carbon will be not within the positive species. Like here, look, I'm going to break down the bond between carbon and alpha carbon will be getted as a free radical and another species as acylium ion. So if alpha carbon not will be within the positive species, this type of a cleavage will be alpha. But if the alpha carbon remain with the positive species, that means the type of a cleavage will be not alpha cleavage, it will be beta cleavage. So in case of beta cleavage, like here, either as homolytic or heterolytic, it's not differ. The breakdown, not the bond between alpha carbon and active group, no. The bond that is going to break down will be between alpha carbon and beta carbon. Look here, the alpha carbon will be remain with the positive species. This type of a cleavage will be as in case of a primary alcohol, which led to the formation of oxonium ion or primary amine. Look here, that's nitrogen, the active group. If I going to carry out alpha cleavage, I should break down the bond between heteroatom or the active amino active group and the neighboring carbon, which is the first carbon, or by another meaning alpha carbon. But when I found within the fragments, I have the alpha carbon, so I should break down between alpha and beta. I'm going to carry out alpha beta cleavage. By another meaning, alpha carbon will be remain and the beta carbon will be removed with the remaining structure as a free radical. Another type, we are going to have it as trobolium ion. Trobolium ion, I going to get it, and it give me so stable fragments, give me a sharp or high hist intense peak, which in major type considered as a base peak in case if the benzene ring bonded to carbon. By another meaning, if I have benzylic position with my compound. First of all, I going to have benzylic carbocation, and then I going to have expansion with the ring in order to the formation of 7-member ring, which I name it as trobolium ion. The trobolium ion will be further degradation because the molecular ion, as I said at the beginning, it's unstable and it's going undergoes further fragmentation to form another fragments. So it's going to undergo the fragmentation and lose acetylene group, CH triple bond CH, which equal to 26. And by another meaning, the 7-member ring will be converted into 5-member ring. This 5-member ring will be again undergoes the losing of another acetylene group by another meaning, which equal to 26, and form the triple or the tri ring. In case if I have benzylic position with another substituted group, like if I have methyl group, so I'm going to take the corresponding substituted trobolium ion, which is equal to 90 plus what equal to another substituted group. So the trobolium ion, which will be equal to 90, and the substituted group 15, 90 with 15, so I'm going to have 105. But if I have CH3, but here instead of methyl group, I have hydroxyl group. That's mean 90 plus 17, which equal to hydroxyl group. So I'm going to have here peak, which is equal to 107. So in case if I have substituted trobolium ion, I can carry out the fragmentation in two cases. Either I'm going to remove the another substituted group and I'm going to have and substituted the trobolium ion, which is already undergoes further degradation, just as I explained it here, by losing the first 26 and the another 26, and the another type that I remaining the another substituted group, and I going to have substituted trobolium ion, which is in turn going to give me substituted 5-member ring after the losing of it 26, and this substituted 5-member ring after the losing of another acetylenic group will be result in the formation of substituted tri-member ring. I have so important type of rearrangement, which we can say it as Mcliferty rearrangement. What we mean by Mcliferty rearrangement? Mcliferty rearrangement, that's mean I'm going to have Mcliferty rearrangement, that means I have here carbon, second carbon, third carbon, that's alpha carbon, beta carbon, gamma carbon. The gamma carbon should consist gamma hydrogen. So the condition which should be available within the compound to give me this type of Mcliferty rearrangement, the type of Mcliferty rearrangement should consist heteroatom, pi bond, and gamma carbon which contain gamma hydrogen. How I can carry out this type? I can carry out this type of rearrangement in this way. That's oxygen, carbon, alpha carbon, beta carbon, gamma carbon with gamma hydrogen. First of all, gamma hydrogen will be on heteroatom, and the double bond between heteroatom and carbon will be between carbon that bonded to heteroatom and alpha carbon. And I'm going to break down the bond between alpha and beta carbon, and this species will be removed as a neutral species due to the formation of double bond between beta carbon and gamma carbon. Like here, look, that's alpha carbon. I don't care what the type of atom here, alpha. It's not important. It may be carbon or oxygen. It's not important. The important thing, I have heteroatom, double bond, and gamma carbon, which should consist gamma hydrogen. In some cases, I have no heteroatom within my compound. It also gives me Mcliferty rearrangement, as we are going to see later. That's here, as I explained it for you before, that alpha carbon will be on the heteroatom, double bond will be between carbon of heteroatom and the neighboring carbon, by another meaning alpha, break down the bond between alpha and beta, and the formation of a new double bond between beta and gamma. As I said before, this type of rearrangement is so important one. Like in case here, if I have benzylic structure, العفو دكتورة سليمة، إن قلب الشارت لو لا.
نعم دكتورة تغريد. اوكي واضح الشير مالتش والتقليب واضح.
شكرا حبيبتي. شكرا حبيبتي. شكرا دكتورة. Like here in case of benzene ring, which consists this substituted group. This substituted group, as I said before, I don't care about this atom. Just take care about the carbon, or by another meaning, on a gamma position, which should be as carbon contain gamma hydrogen. In this case, I'm going to have Mcliferty rearrangement, even if my compound consists no heteroatom. The same in case of alkene. Can the Mcliferty rearrangement give me sharp indication about the type of my compound, or can I use it to differentiate between the type of compound from the another compounds? The answer will be yes. Look, in all the cases of tribolium ion rearrangement, the olefin or an alkene is going to be removed, except in case of alcohol. In addition, for the removing of alkene, I'm going to remove water molecule. So if the resulted compounds or the resulted fragmentation or the resulted chart indicate the formation or the peak, which is related to the elimination of alkene plus water plus water molecule, that's mean within my compound, I have alcoholic hydroxyl group. We have retrodiol alter reaction, which is considered as a reversible reaction between alkene and dienes. This type of reaction will be in case if I have a structure which is as an allylic position or cyclic structure consists pi bond. In this case, the reaction will be, as I said at the beginning, electronic bombardment. Then I have this molecular ion. The molecular ion undergoes this reaction either by the mechanism of one electron or the mechanism of two electrons. Is there difference between them? The answer will be yes. If I carry it out as one electron, that means the substituted group will be not within the positive species. But if I carry out the mechanism as two electrons, that means the substituted group will be within the positive species. The elimination, by another meaning, the losing of a neutral like dehydration of alcohol, which is resulted to the formation of this cyclic structure. As all of us know that hydroxyl group as a strong group, when it's going to be removed, it will take the bond and the proton will leave the compound without its bond. So here we are going to have carbocation, and this bond is going to form cyclization due to the nucleophilic attack here. And this compound, which consists of carbonyl group, according to first losing of carbon monoxide, and then the second losing of carbon monoxide, are going to convert the structure from consist two carbonyl groups into this conjugated system. What in case if I have alkenic compound and I have allylic position? Allylic position, what we mean by allylic position? I mean by allylic position, the first carbon that bonded to carbon, double bond carbon. This carbon, double bond carbon, and that's the first carbon that bonded to it, and the same for this. The cleavage will be from the side that led to the formation of allylic carbocation, which is stable due to resonance. And in case if I have substituted ring or substituted benzene, I can carry out this type of fragmentation either according to retrodiol alder reaction or removing R group. Whereas in case if my compound consists heteroatom, it favors to be carry out the fragmentation as alpha beta fragmentation, like in case if I have here oxygen, I'm going to carry out alpha beta fragmentation to get the oxonium ion, and also I can carry out alpha fragmentation. Can I use mass to differentiate between two types of isomers? Look here, if I have cis 2-bentene and trans 2-bentene, the two charts will be similar together. So I cannot use mass to differentiate between two isomers, but I can differentiate between two isomers, of course, by using NMR. Can I use mass to differentiate between two expected structure, like in case if I have a pentanone? What is the probabilities of isomers of pentanone? Either the carbonyl group will be located at position number 2, so the type of compound will be 2-pentanone, or located on carbon number 3, so it will be 3-pentanone. Look here, that's the carbonyl group. Carbonyl group, I should put in my mind, I'm going to have a helium ion. So if I get with my chart the appearance of two peaks related to a helium ion, that means I have the formation of two helium ion. But if I have with my chart the appearance of one acylium ion, that means I'm going to have one acylium ion, because in case of 2 pentanone, the R group here not similar to this. Here I have position of unsimilarity. It's not the same. But in case of 3, here I have ethyl and ethyl. So in case of 3, I'm going to have one acylium ion. But here I'm going to have this type of acylium ion, and another type I'm going to have this type of acylium ion. In case of ketoprophene, of course, I can indicate the appearance of ketoprophene from IR and from NMR, as proton NMR, as carbon-13 NMR. I can indicate it by UV, because here I'm going to have deprotonation and increasing of lambda max and Emax, and also by mass. How I can get it by mass? By mass, I'm going to have the appearance of peak that related to 77, which indicate that my compound consists benzene ring because 77, 78, 79 refer to benzene ring. Whereas in case of the appearance of peak related to 209, that means I'm going to have decarboxylation, which give me improvement that I have carboxylic group. 105, that means I have type of acylium ion, and the same in case of 177. Thank you for all of you, and my special thanks for Dr. Kauthar. You are so wonderful person, Dr. Wafa. Dr. Salima, I don't found the sufficient word to say thank you for you, but I just want to say to you that I'm so lucky to have such person within my life like you. Thanks for all.
شكرا جزيلا دكتورة تغريد. السادة الحضور إذا أكو سؤال دكتورة تغريد معكم للإجابة على أسئلتكم. السادة الحضور إذا أكو أي سؤال دكتورة تغريد موجودة معكم للإجابة على أسئلتكم. شكرا للسادة الحضور، وشكرا دكتورة تغريد على محاضرتك الرائعة والمفيدة. نتمنى لك مزيدا من التقدم إن شاء الله في مجالك العملي.
شكرا حبيبتي، تسلمون.
أتصور عندنا دكتورة أزهار عندها سؤال. دكتورة أزهار تفضلي. دكتورة أزهار. شكرا دكتورة تغريد.
العفو دكتورة، شكرا جزيلا.
وشكرا جزيلا للسادة الحضور، ومزيد من التقدم إلى دكتورة تغريد. شكرا جزيلا
حبيبتي دكتورة. شكرا.
في أمان الله للجميع.
مع السلامة.
مع السلامة. الله يعافيك.